Okay, so now I'm going to discuss about problem 7.14. Okay, and in this particular problem we have a amplifying circuit using a BJT transistor, and we basically want to decide what's the minimum value of the VCC up here. So what's the minimum value of VCC? So we can represent sine wave at the output, so we can consider this one here as our output with an amplitude P. So P is the amplitude of our sine wave at the output, um, without the BJT entering the saturation or cutoff, and to have the largest possible voltage gain. Okay, so in this particular circuit we know that the voltage gain AV is equals to, so it's inverting amplifier, right, minus VCC minus VCE divided by the thermal voltage. So that's the voltage gain that we have in this particular circuit. Now the thing is that the conditioning for this BJT to work as an amplifying device, or to have this circuit operating as an amplifying circuit, we must have this BJT here working in the active mode region, right? So we need this one here, this PN junction here, to be forward biased, and we want this one here to be reverse biased. Now, one thing that you have been noticed here in this circuit is that we have capital V, capital B here. So let me use a different color to make it more, to highlight this one here. So we have a capital V, capital B, E. We have a small v, small b, e, and we have a small v, capital B, E. So one thing to understand this amplifying circuit is that this small v, capital B, E is the sum of the bias voltage, right, VB, capital V, capital B, plus the input signal that we have in this amplifying circuit, which is a small v, small b. So this one here is the voltage that we use to bias this PN junction here at the base in the meter, right? And VBE here is the input signal that we have. Okay, so we use VBE here, but it could be like a signal that's coming from a sensor or another like measuring system. And VCE here, so small v, capital CE, is the sum of VCE plus this small CE here. And this is actually the output that we want, okay? So it's the small signal that is varying at the output, or this one here, it should probably be an amplification of this signal here, right? And this is the voltage that we get at the collector from the biasing circuit. Okay, so this is VCE, the the voltage that we get from the biasing circuit. Okay, now if we go to the VCE VBE plot down here, okay, so we have this behavior here. So if we get a VBE that's less than 0.5 volts and a VCE that's less than 0.3 volts, right, we are operating in this cutoff region here, okay? And even if we don't have, we might have like a VBE that's even greater than 0.5, but if we are below this red line here, 0.3 volts, we are in this region that we call cutoff region. Okay. Now, if we increase VBE, okay, to be 0.5 volts, and by increasing VBE, we can just increase this voltage source here to forward bias, we guarantee that it's going to be greater than 0.5. So that PN junction here is going to be forward biased, right? And because VCE here at the output, okay, it represents the output signal in the amplifying circuit, and we want to have like a sinusoid at the output, we need to define a VCE here that allow us to have this oscillation here, right? So I'm representing this signal here. Actually should go even lower than that, so let me go up here and down here. Now remember that this amplitude here at the output is actually P, and same here, but negative P. So the value of VCE that we must have to bias or to have our circuit, to allow the circuit to to represent the output signal with a peak voltage of P, is indeed VCE equals to the peak that we have, right, P here, plus this 0.3 volts, right, plus this 0.3 volts, which sometimes is VCE SAT. It is referred as VCE SAT. Okay, so that's the voltage, the potential difference collector emitter that we must have to be able to represent this VCC, this peak voltage in the negative cycle, right? In this negative cycle here. Because if we don't have this VCE equals P plus VCE SAT, eventually if this peak, suppose we don't consider this VCE SAT here, eventually this negative cycle will cross this red line down here, and at these particular values of the output voltage, we won't be able to represent at the output here, because then the diode, I mean the BJT, is going to be operating in the cutoff region, and it's just it turns off. So we won't be able to represent this negative sign here, this negative part of the output. Okay, so we need to have this VCE, right? This capital V, capital C, ESP plus VCE SAT. Okay. Now, if you look at the at VCC here, we also must be able to represent this P here, right? So if we go back to the amplifying equation, so the gain AV equals to minus VCC, VCC, sorry, let me erase here, VCC minus VCE divided by VT, right? If we rearrange this stuff here to describe this VCC, we get that VCC is equals to VCE plus the magnitude of the voltage gain times the thermal voltage. And why I'm considering the magnitude of the voltage gain? Because if you look up here, this basically corresponds to this positive part here, right? Because we might amplify in the negative, so we are inverting the input, but we also have this positive region up here. So that's why I'm considering the magnitude. So our VCC, it must cover this VCE here, that's the peak, plus the saturation VCE, and that gain AV times VT, that's caused by the amplification. Okay, so if we substitute this VCE using that analysis up here, right, we have that VCC minimum, the minimum value of VCC is actually VCE saturation plus the maximum amplitude that we want to represent at the output plus AV VT. So that's the minimum value of VCC. Okay, so if we know our VCE sat, we know the maximum amplitude that we want to represent, and we know the gain, we can calculate this minimum VCC here. And that's basically the second part of this exercise. Okay, so in the second part of this exercise, we have several values of AV. So let me go down here. So we have several values of AV, the voltage gain. We have the maximum amplitude that we want to represent at the output. So this is volts per volt. It's a voltage gain. The peak amplitude is just volts, right? So basically to calculate the VCC that we need, okay, we need to calculate this AV times VT and VCC minimum. And because you want to make sure that the circuit operates properly, we will round, as per requested by the problem, we will round this VCC minimum to the nearest 0.5 volts. Okay, so our VCC here rounded after we calculate VC min. Okay, and remember, if the problem doesn't say any temperature, you always consider VT equals to 25 millivolts. So let's take the first value. So it's minus 20 the gain. It says that the voltage gain when that it's minus 20, and that the peak voltage that we want to represent at the output is 0.2 volts. Okay, so if we calculate minus 20, or the magnitude, which is 20 times 0.2, it's not this 0.2, is, sorry, it's 20, magnitude 20 times this 25 millivolts up here, right? It gives us 0.5 volts. And if we substitute this peak at the output in this AVVT and consider VCE sat as 0.3 volts, we get a VC min. So if we substitute up here in this equation, right, we know all those values here, here, and there, we get a VC min of 1 volt. Okay, and you could use 1.5, or let's just round to the nearest integer here, which is going to keep that as 1 volt. Okay, now we have several combinations of voltage gains, so I will just show you one more, and then the other ones you can calculate yourself by just applying the same rules. So let me pick one here that is, so we know that the voltage gain, it's minus 200, and the peak voltage that we want to represent at the output is 1 volt. So if we take this 200 multiply by 25 milliamps, we get 5 volts at the magnitude AV times the terminal voltage, which gives us a V mean here, VCC mean of 6.3 volts, and then we can round to 6.5. Okay, so basically this is the analysis for this problem. So that's what we want to happen. Okay, we want to represent this maximum voltage, this maximum peak voltage here at the output. This is the voltage gain equation for this particular amplifying circuit using a BJT. And based on the analysis of the VCE and VBE curve, we define that the minimum value of VCE that we want to have is this VCE here equals to the peak voltage that we want at the output plus the saturation voltage. So we need to overcome this VCE sat here to guarantee that once you have minus P here, it doesn't go to the cutoff region, so it doesn't turn off the BJT. Once we substitute this VCE at the equation of the voltage gain, we basically establish our VCC minimum here. And with that equation, we can calculate what's the minimum value of VCC for several choices of gain and output peak voltage.